Okay, so with these two postulates, okay, that the electron orbits are stationary and therefore don't radiate, the electron orbitals, and then the orbital angular momentum of the electron is can only take on discrete quantized values that are integer multiples of h bar, Planck's constant divided by 2 pi, um, then this is how Bohr proposed to get around the problems that we outlined on the previous view graph. So let's see how these two postulates actually make things work out. Okay. So, but before we do that, we should discuss the sort of plausibility of these two postulates that Bohr put forward. Okay. And to do that, we recognize that at this time uh, uh, there was already the concept of de Broglie's concept of matter waves. Okay, and so we can think of electrons as having wave-like properties. We've discussed that extensively in previous lectures. And so if we think about this path that these sort of black dotted line that I'm showing here with radius r, and there's the nucleus in the center. This would be sort of the classical orbital path of an electron, if we just thought of it as a particle in a planetary system as we've described. Okay, but now we can think of the electron as actually being some sort of wave, and if we basically say that the wave has to be confined to the wave is confined to this classic orbital trajectory, this circular orbital path. Okay, then we can see that the wave can actually have to take on different shapes. So, for example, we can have this shape, we can have this shape, we can have this shape, and what we notice here is that on this top one is that the electron spends part of its time outside the classic circular orbital trajectory, and half of its time outside and half of its time inside. Okay, and here we see that it spends a quarter of its time inside, and then a quarter of its time outside, and then a quarter of its time inside, and then a quarter of its time outside. And then here we see that it spends a sixth of its time inside, a sixth of its time outside, a sixth of its time inside, a sixth of its time outside, a sixth of its time inside, and a sixth of the time outside. Okay, so if we actually think about, if we now take the circumference of this circular orbital trajectory and stretch it out into a line, okay, then the wave-like nature becomes more clear. So here we have that if we imagine that the up direction is when the electron is outside its outside the classic circular orbital trajectory, and the down direction is when it's inside, then we see that this trajectory corresponds to this. So this distance from here to here is the circumference of this classical trajectory, 2 pi times r. And now we see this wave, now we see clearly the wave-like property. And the wavelength here is, one wavelength fits into the circumference, 2 pi r. So we have lambda is equal to 2 pi r in this case. In this case, we have 2 lambda is equal to 2 pi r. Again, it spends a quarter of its time inside, a quarter of its time outside, then a quarter of its time inside, quarter out, quarter in, and that's what we've shown here. So 2 lambda is equal to 2 pi r, and here 3 lambda is equal to 2 pi r. And so if you put it all together, right, what you see is that n lambda, the rule is that an integer multiple of a wavelength is equal to 2 pi times the radius. Okay, again, n can be equals 1, 2, 3. So we've now sort of quantized this wave, this matter wave, this electron wave in its orbit. Okay, and so again, we can now identify this with n equals 1, this with n equals 2, and this with n equals 3. All right, and so we can use this now to calculate the energies and the radii of the electron.